Welcome to AP Podcast 13.1. This is on chemical equilibrium. And guys, this is a very big topic in the AP curriculum. This ties in, or we can tie in, kinetics and thermodynamics into this topic and really get a good view of what's going on with the reaction. So let's look at this first thing I've got here, this little definition on what it is. It's the state where the concentrations of all the reactants and products remain constant at a particular time. Now, this is a reaction where you build up some products and then the level of product starts to increase and it starts going backwards towards the reactants. We are so used to chemical reactions where you guys have got A plus B and it yields C plus D. And we learn how to balance it, and we learn how to predict it and all that. And we don't ever think of what's going on, which is actually, in certain reactions, C and D will go to A and B. Now, from our standpoint, if we're looking at a beaker, it looks like nothing's going on. It's just this liquid, and it looks pretty static. However, on the molecular level, there is a lot of work going on. There's reactants are going into products, and products are going into reactants. And probably the best analogy I can give you is if you think about our own town, Tacoma, and you think about our Narrows Bridge. Right here's some amazing Richardson artwork. Narrows Bridge. And then over here we have Gig Harbor, right? And during the morning, there's a lot of cars going this way, right? A lot of cars going this way. And only one car going that way. All right, so that's happening. And then throughout the day, there's cars going back and forth. And then in the evening, there are a lot of cars going this way and only a few cars going that way. Now, from the bridge's standpoint of view and where we're watching, there's just constant activity. Cars are going back and forth, and sometimes it's greater one way and sometimes it's greater the other way. But if we were to look at the population on either side of our bridge, and we were to take the population during the day, we could say that it's probably staying relatively the same, even though there's cars going back and forth. All right, and so that's kind of like a big analogy to what's going on the molecular level, and hopefully that makes sense. Something that makes sense to me. But let's move on to the next thing. So this. When we talk about dynamic equilibrium, I've kind of already alluded to this. We've got a reaction going forward, right? A plus B is going to C and D. And as this builds up, as C and D gets bigger, we get more and more and more, eventually the reverse reaction starts happening. And so C and D turns into A and B. And this will happen until you get an equal rate. And so I've got a little diagram, picture of it for you. Hopefully you can understand what's going on. Imagine the forward reaction. So here are our products right here, or our reactants right here. They're reacting, and as the reaction's going, the level's going down, right? But as the amount of reactants are decreasing, the amount of products are increasing, right? So here's the products, here's the reactants, and eventually we get to this point where the number of reactants and products is the same, and that's what we call equilibrium. Super important concept, and again, we've got to get this idea that the reaction is going both ways. All right, now in order to wrap our brain around what's really going on in equilibrium, we have to think of a couple things. When we talk about equilibrium, we talk about the rates being equal. That means the forward reaction and the reverse reaction are equal. However, the concentrations are not. In other words, let's say for A and B, I start out with 1 molar. We'll make it easy, right? And it reacts, and we get some C and D. And let's say we make 0.7 molar and 0.8 molar, something like that. And who knows what these are going to be. But the important thing is you can't think that the concentrations are going to go until everybody's 0.5 molar. That's not the way it works. All right, that's super important that you get that down. We're not talking about the concentrations. We're just talking about the fact that the number of products and reactants are both going and it's at an equal point, whatever it may be. Now, it turns out, and we're going to get into this in a little bit, the shift could be more toward the product side, or it could be more towards the reactant side. And if you remember way back when we talked about activation energy and reactions going, okay, if you've got a low activation energy, maybe that reaction goes really fast. And if you have a higher one, maybe it's a slower one, that kind of thing. So the rate's really going to be determined by the activation energy and our original concentrations. But the important thing is when we get to equilibrium, when we get to that point, whatever these concentrations happen to be, all right, whether it's that and that and that, whatever they happen to be, that number doesn't change. And I'm going to be able to show you very easily mathematically how that works. So let's look at our next slide, because the next thing is super important. This is called the law of mass action. And the law of mass action is super important. And so there's a few things you need to understand. Basically, it's a division problem, and you're taking the concentrations of the products over the concentration of the reactants. And so if we look at this reaction here, these little italicized letters there, that has to do with the coefficient. And so the coefficients are going to be then turned into superscripts when we write this over. So if you look at this law of mass action, we have the products raised to some power divided by the reactants raised to some power. Now, we're not dividing letters by letters, right? So look at these brackets. These brackets right here tell us its concentration. So whenever we do these problems, we're always going to have some concentration value of some molarity. And unless we're doing a gas law problem, then we'll have some kind of pressure. But for right now, we're going to be dealing with some concentrations. And then this K right here, this K is called the equilibrium constant, and that's going to have a lot of importance down the road, and we'll get to play around with it. It'll make a little more sense. Now, when we're writing a reaction, and how you know it's an equilibrium reaction is you're going to see this double arrow. That means we've got reactants going to products, and products going to reactants. So that's some basic stuff, and now what we're going to be able to do is just to use that equation to figure out what's going on with the reaction. So our first step is just to be able to write out the equilibrium expression. And so here's a reaction up here. We've got a 4 ammonias plus 7 oxygen gives us 4 NO2s and some waters, right? And so if I'm going to write products over the reactants, here's my products right here. So those are going to go on top. And notice the 4 here goes right there. And the 6 here goes right there. So there's my products over the reactants. And again, you could see right there the coefficient becomes a subscript. Okay. Now, we're not putting in numbers yet, but that's okay, because what we're really doing is we're making sure that we can write this out. So what I'd like you to do is just pause the video and answer these 2 questions that we have right here. All right, is that what you got? I'm hoping it is. You can see that I put the products of NO squared because of that right there, times N times O on the bottom, that equals some constant. And the same one here, NO2 squared on the top and that on the bottom. Okay. Now another thing that's common in the AP curriculum is sometimes they want us to play around with this constant, and there are just some basic rules that we can manipulate the K. And once we learn these, this becomes pretty simple. So let's look at the playing with K. Now, if you have the reaction in the reverse, right, and I still did the products over the reactants like I did before, A and B would be on top and C and D would be on bottom, right? Now, rather than rewriting that equation, recalculating things out, if you know what the K was for the reaction where A plus B was going to C plus D, well, the nice thing is, to make this quick, you can simply take the reciprocal of that and get that answer. And so it's a question that kind of pops up every once in a while. They'll go, okay, here's a reaction. What would happen if you did the reverse? Well, if you take that value of K, whatever number it is, and you take the reciprocal, you'll get the answer. So that's kind of handy. So let's look another way we can play with K. Now, in this situation, what we have is we've multiplied some kind of we've used an integer to multiply the whole reaction by something. If you recall Hess's law, remember sometimes we would multiply a whole thing by 3 or whatever. Well, if you do that, and you wrote it out, it would look like something like this, right? Which is kind of messy. You don't want to have to do all that work. Well, it turns out that if you think mathematically and you bring the n out here, right? If you just take k to the n to raise it to some power, you'll get the same value. And so again, another easy way to take something and find the answer to it. So let's calculate this k. Now, if we look at this reaction right here, here's our reaction right there. We see this one up here, and we know that the constant equals 0.13. So they want us to calculate the value of k. Well, let's look at what we have here. We've got a half of n, half of 3, and that. And if we look at what they did to this equation, it looks like they cut everything in half, right? So instead of 1, it becomes a half, 3 halves, and then 1. So basically, what would happen to k in this situation, we would have k equals 0.013, and what we're going to do, I mean, if you raise something to a half power, if I take k and raise it to a half power, what is that? That's a square root, right? So if I just take a square root of 0.013, I get an answer of 0.114. Okay, so that would be the answer to that problem, right? Let's look at the other one. Now, what's going on here? It looks like we have the reverse of this, right? So if we have the reverse of this, k equals the reciprocal of k, right? So if I take 1 over 0.013, I get a value of 76.9. Okay, not too bad. It's important that you could play with this, but again, once you understand how that k works versus the equation they give you, it could be a very reasonable problem. Okay, so here we go. Let's move on. Now, let's talk about k a little more because it's, of course, super important. K is a constant at any temperature. However, what's super important is that it's only constant at that temperature. Because imagine, I mean, think about kinetics. Think about thermodynamics. What does temperature do? It causes molecules to move faster, and therefore the reaction rate's going to go quicker, and that's going to cause the equilibrium to shift one way or the other. So they are going to always give us a temperature, and it's only constant at that temperature. Now let's look at this bullet. The equilibrium concentrations don't have to be the same, only K. And so what that tells you is if I have any kind of reactants, and it's going to be an equilibrium, it doesn't matter what their starting concentrations are, but at the same temperature, you're always going to get the same K. And that's really hard to imagine, but we're going to do some math to show that to you. But that equilibrium is going to be set at that temperature. And when we do equilibrium, we usually don't have a unit. And if you can imagine, if you think about the products over the reactants, and you can see all these kind of exponents we have up here, potentially, it would be really odd. So there's no units for K. It's just a number. And that, we're going to get a real good feel for what that number means. So let's practice doing this using the law of mass action and see what kind of values we get. So here we have a reaction. Good old Haber process making ammonia, and they use this quite often. And notice we started out with 1 molar concentrations, right? And then we let the reaction go until it got to a point of equilibrium. Again, we've got this double arrow, so we made some products, and then we got to a point where the products went back and started making reactants. And at equilibrium, we have this point right here, all these 3 values. So let's write this out. Actually, what I'm going to do is I'm going to write it out, plug in the numbers, and then show you the answer just to save some time, because I know this video is getting a little... Alright, so I've gone ahead and I've written out the law of mass action right here, and then I've plugged in my numbers, squared the top, multiplied those two, cubed that one, divided them all out, and I got a K that equals 0.062. Alright, so let's check that against another reaction where we get different concentrations, but it's the same temperature. Okay, now take a moment, go ahead and pause it. We've got the same reaction, same temperature, but notice we're starting with a 1 molar concentration right here of ammonia, okay? And then eventually we get to this equilibrium condition right here, Okay, so everything's right here. We've got these values. Oh, geez, sorry about that. I'm having a little technical difficulties here with my eraser. But at this point, we've got this equilibrium. So calculate it out and see what value you get. All right, did you find that your value for K equals 0.0602? Just like before. But again, what's important? We had different concentrations, but at this temperature, this reaction, notice the concentrations are different, but the K value is the same. So this point right here, I can't emphasize enough. Okay, same no matter what the amount of starting materials are. Okay, at that same temperature. So the equilibrium position, the K for this reaction at that temperature is 0.0602, no matter what the initial concentrations are. Super, super important, because the equilibrium is a position that this reaction is going to achieve regardless of any other factor at that temperature. So, super important stuff. Now, I know this video went a little long, but this was a really good one. So, if you have questions, we'll talk about it tomorrow, and we'll see you next time.